Hey everyone, in this video, I will do a Llama-3 fine-tuning on a custom dataset. And the model I'm going to use is this one, Llama-3 8B, and that's quantized to 4-bit with the bits and bytes library. And as you can see that I'm going to use this Unsloth library for this fine-tuning. So this is the GitHub repository of Unsloth. It's an open source library, and actually the main specialty of this is that it is designed to do your fine tuning super fast. That is, it is very compute efficient. So for example, they have given these numbers. Llama-3 is 205% faster. Llama-3 8B uses 63% less VRAM and so on, and 70B is 183% faster. And they have given a collab example, this one, and I am pretty much going to use this one. It's a very standard code examples that they have given using their library. I am only going to make very slight changes in some of the places. Now, as a first step, you need to install Unsloth, definitely. So you can just install it by running the simple command pip install and pass all these things. That is Unsloth, the collab new, and also the GitHub repository link of Unsloth. And after that, depending on the version of your current system, that is the compute capability version of your current system, you need to install some more libraries. So here, what I'm doing is CUDA.getDeviceCompatibility. This method returns the major and the minor CUDA compatibility of the current device, where major and minor are integers representing the major and minor revision numbers of the compute capability. The major revision number, that is the first element here, is the most relevant for determining general capabilities. Higher numbers typically indicate support for more advanced features and better performance. And the compute capability is a version number that corresponds to a specific GPU architecture's features. Here, the major version number of the compute capability is extracted and checked. So, for example, if the major is 7 and the minor is 5, then your compute capability is 7.5, because in the context of CUDA, the compute capability is represented as major.minor. And next, we need to import the most important modules from Unsloth, which is a first language model, and then define some of the hyperparameters. Max sequence length, here I'm keeping the default to 048, but you can choose any depending on your situation, because Unsloth support rope scaling internally. And D type is none for auto detection actually. So float 16 for Tesla T4 V100 and bfloat 16 for Ampere plus GPUs. And load in 4-bit true, that's because I'm using 4-bit quantization to reduce memory usage. And if you keep it false, then obviously it will not use the 4-bit. And all the 4-bit models that Unsloth currently has are this one, Mistral, then I have Llama-2, Gemma 7B, 2B, etc. and for Llama-3 8B. And this is the one that I'm going to use. And then just a regular code that we do for any transformer model and tokenizer is what I need, and I can do that by applying or invoking fast language model .from pretrained, and then pass your model name, max sequence length, D type, load in 4-bit. Now, before proceeding any further, I just want to talk about this fast language model that we are using here. So currently I'm looking at the source code of Unsloth library in their GitHub repository, and under the loader, under models and then loaders, you will find that this fast language model is being defined here. So this fast language model inherits from fast Llama model, and which basically just means that fast language model is a subclass of fast Llama model, and it inherits all methods and properties of fast Llama model, while also having the ability to add new methods or override existing ones. Now, remember that these all the magic of fast execution and super efficient compute that is going to be used in my fine tuning, that's coming from this particular class. And what is a general under the hood technique that fast language model implements to get those efficiency? There are quite a few reasons indeed. For example, customized attention mechanisms. So Unsloth leverages the XFormal library for memory efficient attention calculation. This library offers optimized implementation of attention algorithms, particularly beneficial for large models with extensive memory requirements, because we are going to be using pretty large models here. Like 8B will take, normally it will take almost 12 GB to 16 GB of your VRAM, but here it will not when using Unsloth, and also I'm using quantized 4-bit. Then another technique this library uses is fast attention 2. This is an optional for this class. So if you're using it, that means Unsloth will integrate the flash attention 2 technique for you for further attention speed up. And then the next technique these particular class implement is KV cache optimization. So for fast inference, Unsloth implements KV caching. This technique stores key and value attention tensors from previous tokens, reducing redundant calculations and significantly accelerating the inference process. Then also another technique used is GQA, that is grouped query attention. So Llama models used group query attention, where the attention heads are divided into groups. So Unsloth's code efficiently handles this grouping by expanding and reshaping the K and V, that is the key and value tensors, to align with the grouped structure. And this allows the attention mechanism to operate on the groups independently, achieving the desired optimization. Then Unsloth also uses SWIGLU, which replaces the standard activation function in MLP layers with faster custom implementation, maintaining accuracy while reducing computational overhead. And after I define my model and tokenizer, then I need to apply or add the LLORA adapters. So we only need to update 1 to 10% of all the parameters. So here, that's exactly we are doing. Again, I'm using first language model and then to get PEFT model. And here you supply all your hyperparameters for your LLORA config. For example, R16, choose any number between 0 and then higher number like 8, 16, 32, 64, 128. Target models, these are your target models which contribute most to your calculation, attention calculation. Then LLORA alpha, keeping it at 16, LLORA dropout 0, and 0 is the most optimized one. And then use gradient checkpoint, that's Unsloth, or true or Unsloth for very long context. And use RS LLORA false, and LOFTQ loft Q config is also none. And okay, so that's how my model is getting the LLORA adapters. And then some more things that I need to define. Actually, the next step is just prepping the data. So this is an instruction fine tuning. So I need to apply. Okay, the dataset that I'm going to use is this one, Alpaca cleaned. I'm going to show you the dataset in a second. It's a pretty famous one in Hugging Face dataset repository. And because it's an instruction fine tuning, so I need to give this model instruction dataset. That is, it will have an instruction column, an input column, and a response column. This input column will not be that important, and actually we will see that it is empty for this particular dataset for many rows. So, and the prompt is like this. Below is an instruction that describes a task paired with an input that provides further context. Write a response that appropriately completes a request. Okay, now let's quickly check out the dataset. And this is my dataset, and as you can see, we have an instruction column right here and an output column, and the input column at many rows, at many places, is just empty. So if we just go to viewer to check out the actual data, okay, give 3 tips for staying healthy. This is my instruction, and then it gives 3 tips indeed, number 1, number 2, and number 3. So that's how this whole dataset is structured, and it has got 51.8 thousand rows for trained dataset. That's quite huge. And before supplying that data to the model, we need to structure it slightly differently, because we cannot supply the data as it is. We have to have this particular prompt format. That is, there will be an instruction for each of the rows saying exactly this particular instruction. That is, below is an instruction that describes a task, so on. And then there will be my actual instruction for that particular row, then the actual input, and then the actual response. Okay. And to get these in this format, I need this little util method called formatting prompts function. It's a very simple one. All it does is that it is processing the data entries from the dataset. That is, these examples represent each of the example, and this example contain 3 fields: instruction, input, and output. It formats these fields into a template string stored in the variable Alpa Prompt, and appends an EOS token to each formatted string. And EOS token, we are defining it here. That is tokenizer.EOS token. So the EOS token is coming directly from the tokenizer, and we have already got a tokenizer previously. That is here. So when we applied from pre-trained, we already got the model and we already got the tokenizer. So now I'm just taking the end of sequence, that is a EOS token from that tokenizer. So basically, with the formatting prompt function, the original dataset, which includes fields like instruction, input, and output, is transformed so that each of these fields is concatenated into a single string per data entry following the specified format in Alpa Prompt, that is this variable. And then the formatted text for each dataset entry is compiled into the list. That is, when I'm doing text.append text, it is getting compiled into a list of text, which is then returned as a dictionary with key text. So this text is my key, and all the list of text is a value. So this dictionary structure is typically used to comply with the requirements of the map function from the datasets library, which applies a formatting function in batches to the dataset with this line right here. So I'm getting my datasets from the load dataset library, and then dataset.map, then formatting prompt function, and badged equal to true. This badged equal to true parameter indicates that the function should be applied to batches of the dataset rather than individually to each item, which can be more efficient for very large dataset. The resultant dataset has a dictionary-like structure where the keys are the fields of the dataset. In this case, text field. Each entry under these keys is a batch of formatted strings of the dataset. So let me show you an example when this dataset, what kind of structure this dataset will take before getting fed into the model. So this is a structure. So what it means is that after processing with formatting prompt function, the same entry in the dataset provided to SFT trainer, that is SFT trainer is a class that we will be applying next right here. So when fed into SFT trainer, would be a dictionary with a single key value pair, and the key is text, the word text, because that's how we have defined it here, that is return text and then all the text. And so the key is text, and the value is a batched list of formatted strings. A single string in that batch would look like exactly this, assuming the EOS token is something like this. Of course, the EOS token will depend on the tokenizer. So you can see the similarity here. That is my instruction, my input, and my response. And there will be, this is just a single example. There will be batch of examples like this before getting fed into the SFT trainer class. So now coming back to our next step is train the model with SFT trainer. And the SFT trainer that we are implementing here is a very standard code. We are just defining all the parameters of this training. So you define your model, tokenizer, train dataset, dataset text field, that is our key value, which is text, max sequence length, etc. Packing equal to false. So here, let's quickly discuss what this packing is all about. So looking at the official documentation of SFT trainer in Hugging Face official doc site. So SFT here, this is the parameter that I'm talking about. So SFT trainer supports example packing, where multiple short examples are packed in the same input sequence to increase training efficiency. This is done with the constant length dataset utility class that returns constant length chunks of tokens from a stream of examples. To enable the usage of this dataset class, simply pass packing equal to true to your SFT trainer constructor. Now, this is this example, but remember we used packing equal to false. Let's see why. And the reason is that here we are doing the training only on completions, that is ignoring the user's input. Now, you can read about this in the TRL's official docs, and it clearly actually says that you can use data collator for completion only LM to train your model on the generated prompts only. And note that this works only in the case when packing equal to false. So when you are doing training on completions only, you necessarily have to set the packing equal to false. And train on completions only actually refers to a training strategy where the model's updates are based solely on the generated responses, that is generated completions text, rather than on the full prompt completion pairs. So in traditional language model, that is traditional language model training, both the input, that is the prompt, and the output, that is the completion, are used during the training process. However, when training on completions only, the model focuses exclusively on learning to generate the correct outputs from a given input, ignoring the inputs themselves during the gradient update process. So this completion only approach is beneficial for improving the model's ability to generate contextually accurate and relevant responses based on a given prompt, because here the model's focus is on the output quality rather than the input-output relationship. So by focusing solely on the completions, the model receives direct feedback on the generated text itself. This feedback is based purely on how well the completions adhere to the desired output format and content rather than how well they follow from the input. This helps the model learn to produce better quality and more precise outputs that match expected responses. Also, this strategy of completions-only training reduces the overfitting possibility, because in conventional training, the model might learn to heavily depend on specific cues or patterns in the prompts, which can lead to overfitting. But by training only on completions, the model is less likely to memorize prompt-specific patterns and more likely to develop a general capability to generate correct and relevant content, independent of the specific way a prompt is formulated. Also, in this case, the model tends to develop a more flexible understanding of how to construct responses. This flexibility is crucial for producing outputs that are not only accurate in terms of content, but also appropriately contextualized and nuanced, adapting more effectively to a variety of inputs in real-world applications. So when packing equal to false is specified, just like what we are doing here, it indicates that the data should not be packed tightly together, which is crucial here. So in packed sequences, multiple sequences are concatenated closely together to maximize the use of space in batches, often mixing parts of different examples in a single batch tensor. But given here we are doing the training on completions only, and for completions only training, it's important to keep each completion isolated to ensure that the model's updates are based strictly on the responses and not on any blended data. And the next cells, these few lines is just for getting some GPU stats before starting the actual training. So we need to get the starting GPU memory, the max memory, and that we print. For example, this particular collab is using Tesla T4, so max memory is 14.748 GB, and memory reserved is 5.605. And basically, when you run this particular line here, that is torch.cuda.getDeviceProperties, that will give you a lot of statistics about your current GPU device. All right, now, finally this line, trainer.train, very famous line, and it will take the most time in the entire notebook, because this is where the actual training is happening. And after the training is, again, I am showing the final memory and time statistics. So here again, I make use of those CUDA.max memory, then CUDA.max memory reserved, etc. So I get peak reserved memory is 8.922 GB. Peak reserved memory for training is 3.317 GB. Peak reserved memory as a percentage of max memory is 60.496. So only 60.5% memory was used for this training. And if you're wondering that why we are doing these division by 1024 three times, that's because these numbers that you get from CUDA max memory reserved, it's in bytes. So to convert the bytes into gigabytes, you need to divide the by these numbers, and that is the whole reason here. All right, after this, I'm ready to do the inferencing, the most important part. Okay, here I am going to use these first language model.for inference. This is a special module or method within Unsloth. I will talk about that little in a second, but first let's quickly understand the input format here. So what I'm doing, the inputs here, that is to the tokenizer, I'm passing the actual prompt, but the prompt needs to be formatted as per the Alpa Prompt requirement. And remember, we defined this Alpa Prompt format right here. So we need an instruction, input, and response. So, and it will all start with this initial statement, that is a system prompt. Okay, so here exactly that's what we are trying to achieve. That is Alpa Prompt dot format, and then passing three strings. So the first one is instruction, second one is my input, and the third one is the final response or the completions from the model. And because it's a PyTorch thing we are using everywhere, so return tensor is equal to pt, and passing the entire thing to the GPU device with the CUDA. Then I get models.generate, and to that I'm passing these inputs. Okay. And max new token 64 use cache true, and from that output I'm going to do the decoding process from that output, because it is encoded, and the tokenizer.batch decode outputs, and that is my actual output. And the output here looks like this. So here the whole instruction was continuing the Fibonacci sequence, and yeah, that's my instruction. The input was given as 1 2 3 5 8, and response is this, that is it continued the original sequence into 13, 21, 34, 89, and so on. Okay, so that was the first way. And then another quick example we are giving here with using text streamer. So so you can see the generated tokens, generation token by token, instead of waiting the whole time. And to do that, very small change is required only in a single line. So first you define text streamer with this line, and everything else remains just the same. It's only changes here, model.generate inputs, and then for the streamer parameter I pass this text streamer, and this is the kind of response I get. It's only because only difference is that here I can see the tokens as soon as they are generated. And now quickly talking about these for inference method, because this is another magic of Unsloth library. It is this is what it makes your inferencing so fast. So you can actually go through their source code, then you probably will have a much clearer idea exactly how this is implementing all the faster execution methodology. So basically it disables the gradient computation and sets the model to eval mode first. And then it also deletes any cached fast LoRa weights used during the training. And actually, looking into the source code, we can see, I'm not going into the entire source code right in this video. It has anyway become longer than I expected. So it also implements a paged key value cache, that is this for inference method. And these are all to increase the efficiency of calculation here, because the cache is also resized dynamically as needed. And then this particular method also make use of torch.mv and torch.mathmul operations for the final linear projections, that is LM-head, avoiding a full torch.mm, that is torch.matrix multiplication, when batch size is just 1. This is another contributing factor for the whole calculation becoming so much faster with this method. And after we are done with our inferencing test, you definitely have to save the model and push it to Hugging Face hub if you want. And that's what these lines is doing: model.save pretrained and tokenizer.save pretrained. To save the final model as LoRa adapters, either use Hugging Face push to hub for an online save or save pretrained for a local save. So here I am doing the local save options here, and the two comment out lines are doing push to hub. Okay, and now if you want to load the LoRa adapters, we just saved for inference, set false to true, that is in this code right here. And these are all very standard code. You are again defining load in 4-bit to your whatever you have defined load in 4-bit to be. It's a Boolean parameter. All right, let's move past it. Yeah, saving to float 16 for VLLM. So if you want your inferencing to be done with VLLM, which is a very powerful backend for very fast throughput of large language models, you need to save it in float 16. So here, that's what it is using. That is a model.save pretrained merged. Then you pass your model, tokenizer, and save method. You mark it as merged 16-bit. So these method save pretrained merged, it's coming from actually from Unsloth, but under the hood it is an extension of the standard save pretrained method provided by Hugging Face's transformer library. It allows you to save a fine-tuned model with additional optimizations and options specifically tailored for Unsloth's fast inference capabilities. So this method is exactly the same as the save pretrained method of Hugging Face, except 4 bits weights are auto converted to float 16 with as few overhead as possible. So these save method parameter, you can choose either 16-bit, 4-bit, or LoRa. So here we have first one case, we have chosen merge 16-bit, then we have chosen merge 4-bit, and finally LoRa. And this next line is for GGUF or Llama.cpp conversion. And this is another magic of Unsloth, that is they support it natively. So they clone the llama.cpp and it defaults to Q8_0. And these are just the standard code for doing that. So to save it to 8-bit with Q80, model.save pretrained GGUF. And now you are using save pretrained GGUF. Previously we used save pretrained merged. Okay. So here again, just pass the model, tokenizer, and push to hub GGUF. And then for 16-bit, only difference is that you have to pass another parameter, quantization method. There you pass F16. Then the final one, we are saving it in Q4KM format. So after these models are absolutely saved in Hugging Face Hub, and you can just use them with those standard libraries like VLLM or Llama.cpp or even GUI-based systems like GPT-4 all. You just have to pull those model names to your respective system. All right, with that, this fine-tuning is complete with our initial model that we started off, which was this, that is Llama-3 8B BNB 4-bit, and we trained it on the alpaca dataset. So you can definitely train it with any other instruction dataset. Just need to change your formatting prompt function accordingly. That is, for some dataset instruction maybe something else. So you just need to change this string and the output string, because for some data set it is noted as response or whatever. So yeah, with very minimal changes, only couple of lines here and there, you can do the fine tuning on any other data set as well. All right, with that, thank you very much for watching and see you in the next one.